Couple things I wanted to point out for those of you in Dedella's class, which I know is the majority of you in here. Um, Three things. Thing one, he posted this for you all to see, which is the front page of your exam. Specifically, you should read the instructions just so you like know what's coming at you. But also down here, he's showing you all the formulas he's going to give you. So that's all going to be on the front page of your exam. You should be aware of that. I would point out specifically the definition of the integral as a limit, the fundamental theorem of calculus, parts 1 and 2. The net change theorem, I don't know about that. And then some trig identities down there, and then the equation of a tangent line. So all that's going to be on the front of your exam. So you don't need to worry about jamming those formulas into your head, other than that you should know how to use them. And then the other thing I wanted to point out was, if you haven't seen it already, I have posted a practice exam. It is somewhere in the modules right here. Practice exam one, solutions, and then also a recording of me writing out the solutions. So to that end, I'm not going to be going over a practice exam in class because I don't think that's the best use of our time. We still have other things to talk about. And I said there were three things. Oh, the third thing is the practice problems he posted. So here's the practice problems he posted. Oh, that's smooth. Here's the practice problems he posted. You should definitely do the practice problems your teacher gives you before a test. I would point out one thing specifically. This first problem says use any method, do not simplify. That means don't simplify your answer. But definitely for at least half of those integrals, you want to simplify them before you do the integrating. So don't let that confuse you. Do not simplify means once you get to a final answer where you've like done the thing you've been asked to do, you shouldn't simplify it any further. But definitely simplifying the thing before you get to the final answer is okay and often recommended. I would say specifically for problems B, C, and F, you should be simplifying those expressions before you find the antiderivative. I would also argue for D as well, because there's a trig identity you use for that. That's all I wanted to say about those three things. Let me do this here. Pin myself here. Okay. That thing, 1 second. My plan for today was to talk about partial fractions a bit, and also to maybe do some more examples of some trickier U sub and integration by parts problems. Let me just do one thing. There we go. So, what is this? They still haven't fixed this. It's too bad. I know they've got lots of things to do, but my classroom's the most important. They should do mine first. Cool. All right. So let's do some partial fractions. I should mention that the whole point of partial fractions really isn't actually a method of integration. It's a method of rewriting the integrand so that it's easier to integrate. So really, it's just an algebraic thing you use for integration and for actually other stuff in 21C, which you don't have to worry about. But certainly, we're just rewriting an integral. So let's look at an example like the integral of x plus 3, yeah, over x squared plus 6x plus 8. So to be able to use partial fractions, I'm going to say there are actually 4 things you need to check. 3 of them you actually have to check. The 4th one you should check. So here's the 3 things you have to check. Thing 1, it's a rational function, meaning it's a polynomial divided by another polynomial, meaning you have positive integer powers of x divided by positive integer powers of, I should say non-negative. Technically, you could have just a constant on top, and that would still be totally fine. The second thing that has to be true is the degree in the numerator, or on the top, has to be strictly less than the degree in the denominator. If they're equal, that means you have to do something else. If the one on top is greater, that also means do something else, which is polynomial division. And the third thing you have to check is that the denominator must factor. And then what I'm going to say is before you do any of those things, because this one certainly looks like all those things are true, right? It's a rational function, the degree on top is smaller than the degree on the bottom, and the denominator definitely does factor as x plus 2 times x plus 4. And before you think of any of that, you should check to see if a U sub works. because this one, it definitely would. And so I will point out that when you think of partial fractions, when you see this kind of thing here, you should always be at least trying one other thing first, because in partial fractions is a method of later resort. You don't want to try partial fractions right off the bat, because there's sometimes an easier way to do it. Here, that's exactly the case. If you let u equal x squared plus 6x plus 8, our du is going to be 2x plus 6 times dx. And if I factor out a 2 or divide both sides by 2, 1/2 times du is exactly equal to x plus 3 times dx. And oh, look, we have an x plus 3 times dx. That's our 1/2 du. So here, even though you could use partial fractions here, it's a lot more work to use partial fractions here. So instead, we should definitely do the u sub. We're going to end up rewriting this integral as the integral of 1/2 times du over u. Or if you might prefer, 1/2 times the integral of 1 over u du. Either way, when we integrate this, we're going to get 1/2 times the natural log of the absolute value of u plus c. And then we're going to get 1/2 natural log of the absolute value of x squared plus 6x plus 8 plus c. And we absolutely need the absolute values here because x squared plus 6x plus 8 is not always positive. It's sometimes negative. So again, in general, if you're not sure, you should always just leave the absolute values. There's never any good reason to not write them, or there's never a necessary reason to not write them. Okay. Well, let's actually get to the point, which is that you're not always going to have a u substitution that's going to work out so nicely. So if you had something instead like, something like the integral of x plus 5 over x squared plus 6x plus 8. Now we can see that the u sub is not going to work, because if we made the same choice for u, our du would still be 2x plus 6, and definitely x plus 5 is not a multiple of 2x plus 6, right? You can't multiply 2x plus 6 by 1/2 and get x plus 5. So here we are stuck using partial fractions. And so when we're using partial fractions, we're going to start by just writing the integrand, the inside of the integral, in the partial fraction decomposition. So we're going to rewrite the integrand, x plus 5 over, we're going to factor the denominator, x plus 2 times x plus 4. And then we're going to write that as a sum of fractions with less complicated denominators. So we're going to write this as something divided by x plus 2 plus something divided by x plus 4. The reason we're allowed to do this is because if you add these two fractions together, well, to add fractions together, you have to get a common denominator. So you'd multiply this fraction by x plus 4 over x plus 4, and this fraction by x plus 2 over x plus 2. And that would give us something like this. The only issue is we don't know what's in the numerator. That's what our job is to figure out. So we're to say, well, there's some constant up here, and there's some constant up here. Oh, a different constant. That's a b. We know they're constants because if it was like x to a power, you'd have something that was x over x, and then that wouldn't be the right sort of difference in degrees. So we definitely know they're constants. They're not anything other than constants. I don't want to get too into the details about why they're not, but you should, I don't like saying this usually, but you should just believe me. They're going to be constants, I promise you. There is a slightly more complicated case we'll deal with a little bit later on. Oh, maybe we won't actually. Oh, maybe we will. Actually, most 17B classes don't usually deal with it, but Dedel is not most 17B classes. So, all right. So all we're going to do now is try to figure out A and B are. There's a number of ways of going about this. I will show you the way that I think is the easiest and fastest. The first step should be multiply both sides by the common denominator. So step 1, multiply both sides by the common denominator that is already the denominator of the left-hand side. So by the common denominator already on the left-hand side. I would recommend showing this work, but you don't have to. So I'm going to multiply both sides by x plus 2 times x plus 4. So here's what's going to happen. X plus 2 times x plus 4 times x plus 5 over x plus 2 times x plus 4 equal to a over x plus 2 plus b over x plus 4. All of that also multiplied by x plus 2 times x plus 4. Okay, the point of this step, or I should say, what you should always expect to happen after this step is you shouldn't have any denominators after this step. All your denominators should cancel out. You should be left with something else. On the left-hand side, it's always just going to cancel out perfectly. So x plus 2 times x plus 4 divided by x plus 2 times x plus 4, those divide to 1. On the left-hand side, we're left with x plus 5. On the right-hand side, we're going to distribute this to each of these two terms. When you distribute x plus 2 times x plus 4 multiplied by a over x plus 2, what cancels? What cancels? The x plus 2. So what's left? A times x plus 4. And then similarly, when we multiply this by the b over x plus 4, the x plus 4s cancel, and we're left with plus b times x plus 2. No denominators. All right, step 2. This is where your instructor might have shown you something different. But I'm going to show you the way that I think is the fastest. The fastest way to do this, at least, so I'm going to back up a little bit. This example, it's easy to do really fast. Other examples, it's easy to do the first part really fast, but then you have to kind of switch gears and do the second part a different way. So we're always going to start off by finding as many things as we can as easily as possible. We're going to pick nice values of x. Because this equation, x plus 5 equal to a times x plus 4 plus b times x plus 2, has to be true for any value of x. So pick a value of x that makes one of these two pieces equal to 0. I'm going to pick x equal to -2. Because then -2 plus 5 is equal to a times -2 plus 4 plus b times -2 plus 2. I should point out, I'm writing too much. You shouldn't write all this. You should really just write 3 equals a times 2. Excuse me. You don't have to write b times 0. We know that b times 0 is 0. Similarly, up here, if you're comfortable skipping this step, knowing what's going to happen, that's totally fine. I'm just showing it so everyone can see what's really happening. So here we're going to end up getting 3 over 2 equal to a. And in a similar way, I should also let x equal what? Right. So x is -4. We have -4 plus 5 on the left equal to a times -4 plus 4 is going to be 0 plus b times -4 plus 2. So here we're going to get -4 plus 5 is 1 equals b times -2 or -2 times b. So we're going to get b equal to -1/2. Typically, when you do this, when you're finding a and b or c or whatever, usually all of your values have the same denominator. So if you get like a 1/7 and a 1/5, that's a sign that something went wrong, probably. Doesn't always have to be true, but it's generally pretty true. So now we found a and b. We're going to go back and rewrite the integral as the integral of 3/2 over x plus 2 plus -1/2 over x plus 4. So our integral, let me scooch this up a little bit. There's always this little piece here. Let me move things around just a little bit here because there's one piece that's kind of in the way. So let me do something real quick here. It's a little bit easier to deal with. Sure. Okay. Hopefully that'll work better. But let's not do that. Okay. Sorry. So our integral of x plus 5 over x plus 2 times x plus 4 dx is now going to be the integral of 3/2 over x plus 2. Instead of writing plus -1/2, let's write -1/2 over x plus 4. I personally think you could skip writing this out into two integrals, but I'm going to show you, I'll write the answer and then we'll go back and we'll fill in the missing step here. So we know that the integral of 1 over x plus 2 is the natural log of the absolute value of x plus 2. The 3/2 just multiplies that. So that's going to be 3/2 times the natural log of the absolute value of x plus 2 minus 1/2 times the natural log of the absolute value of x plus 4 plus c. Sorry, that's really smushed in there. Should have used more paper. The intermediate step here that I'm not showing and I don't think you need to show or do, but you can if you want to, is that you can break this up into two integrals. The first integral is 3/2 times the integral of 1 over x plus 2 dx. The second one is minus 1/2 times the integral of 1 over x plus 4 dx. Again, I don't think you need to write this step, but if you want to, you certainly can. Or if you feel like you need to, you definitely should. All right. So definitely you should ask questions if you got them, but we're just going to do some more examples.
Super quick question about, so do you have to condense the answer dividing with natural log?
No, you don't have to condense your answer.
Okay.
And specifically, I'll point out on your exam, many of the problems will say, do not simplify your answer. So you definitely shouldn't do anything more than this, even though you might be able to. Okay. Yeah, sure. Let's look at that. Yeah, sure. So we will look at the integral of 3x minus 8. You probably can't see that. There you go. 3x minus 8 divided by, what have I got here? I'm going to change that up. That's probably going to be terrible, but fine. X cubed minus 6x squared plus 9x dx. Okay, off to the side, before I do anything, I should really just quickly check, can I do a U sub? If I let U equal x cubed minus 6x squared plus 9x, am I going to get 3x minus 8 or a multiple of 3x minus? No, I'm definitely not. Right? If U is x cubed minus 6x squared plus 9x, my du is going to be 3x squared minus 12x plus 9. There's no way I'm getting 3x minus 8 from that. So don't even really need to check. So let's go ahead and see, well, let's see. It's a rational function. The degree on top is 1, the degree on the bottom is 3, and definitely the denominator does factor. So we're going to think about our integrand, 3x minus 8 over, let's start factoring. It's x times x squared minus 6x plus 9, and that factors further, and you do have to factor it fully. So that's going to be x times x minus 3 times x minus 3, or x minus 3 squared. And so now the partial fraction decomposition has a little bit more going on. So what I would point out is so we have a bunch of linear factors here. X is a linear factor. If I say X is a linear factor, if you think, oh yeah, I know the line y equals X, it's a straight line. X minus 3 is a linear factor. Y equals X minus 3 is a straight line. But X minus 3 is a repeated linear factor, right? Because it's being raised to a power that's higher than 1. When you have a repeated linear factor, you have to have that highest power in your partial fraction decomposition and every lesser power. So I need to have x minus 3 squared all the way down to x minus 3 to the first, which is only two things. But still, like, if you had like x minus 3 to the fifth, you would need 5 terms. X minus 3 to the fifth, x minus 3 to the fourth, x minus 3 cubed, x minus 3 squared, x minus 3 to the first. So whenever you have a repeated linear factor, you need to have that many pieces and you have every lesser power down to 1. So here we're going to write this as a over x plus b over x minus 3 squared plus c over x minus 3 to the first. Doesn't matter what order you write them in. I feel like some people do them in the opposite order, but I like to write the highest power first because I'm like, oh yeah, there's the highest power, and then I need all the smaller ones after that. Okay, so I want to say here, no, not really. Next step is the same as before. We're going to multiply both sides of, I should say, of this equation. We're going to multiply both sides by the common denominator, x times x minus 3 squared. I'll point out, by the way, the reason we need all these pieces is because if you add these three fractions together, they still have that common denominator, right? You'd multiply this by x minus 3 squared over x minus 3 squared, and this by x over x, and this by x times x minus 3 over x times x minus 3. So it's still a common denominator here. I should check it on something. Okay. So multiplying both sides by x times x minus 3 squared. Again, I think you can skip right into this next step, but I'm going to write it. I have x times x minus 3 squared times 3x minus 8 over x times x minus 3 squared. It always feels especially silly to write it on the other side, on the left side. On the right-hand side, it's going to be x times x minus 3 squared multiplied by all of that. A over x plus b over x minus 3 squared plus c over x minus 3. On the left-hand side, they cancel. You get 3x minus 8. On the right-hand side, we distribute to each of these three things for this times a over x, the x's will cancel, and you're going to have a times x minus 3 squared. This times b over x minus 3 squared, basically the thing in the denominator cancels, right? So here the x minus 3 squareds cancel. We're still left with a b times x. And thirdly, x times x minus 3 squared times c over x minus 3. One of the x minus 3's cancel, and we're left with c times x minus 3 to the first. I am not a proponent of multiplying this out. Some people are. I think it's not the best use of your time. I won't say a waste, but not the best use. I'm going to do the thing I usually do. I'm going to pick nice values of x. What's one nice, show me on your fingers. What's one nice value of x? Yep, definitely. And the other one is 0. So basically, another way to think about it, it's whatever values of x would make you divide by 0 up here. So 0 makes you divide by 0, and 3 makes you divide by 0. We're going to run out of nice values for this problem. That's okay. So first, we're going to let x equal 3. On the left-hand side, we're going to get 9 minus 8. On the right-hand side, we're going to get a times 0 plus b times 3 plus c times 3 times 0. You don't need to write all the things times 0. So here we're going to get 1 is equal to 3 times b, or 1/3 is equal to b. Our other convenient value is x equal to 0. Plugging in 0 for x, we're going to get 0 minus 8 equal to a times negative 3 squared plus b times 0 plus c times 0 times negative 3. So we have negative 8 equals 9 times a. So negative 8 over 9 is equal to a. I know I said the thing for the last example about how like your fractions typically have the same denominator or easily have a common denominator, right? 1/3 could easily become 3/9. So usually one of them is either a multiple of the other one or they're the same. Okay, but I've run out of convenient values and there's still a value left to find, right? I still need to find c. And what I really, really, really don't want to do, especially because my a and my b are fractions, I would prefer not to pick another value of x. You can do it that way, and in fact, I will do it that way, but to show you how it's not lovely. So, yeah. What am I going to pick for x? I'm going to pick x equal to 1. So you probably might not want to write this down, actually, because I'm going to show you a better way to do it in just a second. So, but if I picked x equal to 1, and I plugged in 1/3 for b and negative 8/9 for a, I'm going to have 3 minus 8 on the left equal to negative 8 over 9 times 1 minus 3 is negative 2. Negative 2 squared is 4. Plus b is 1/3 times 1. Plus c is what I'm trying to find. C times 1 minus 3 is negative 2. That looks terrible. I don't want to solve for c when I have to add fractions together. More importantly, we don't have to. There is a better way to do this. So this is an option, and you can do this, but it only is really a good option if you've got like one thing left to find. If you have multiple things left to find and you've run out of nice values, in general, you should do the other thing I'm about to show you anyway. So instead of doing this, don't do this. Instead, what we're going to do for finding the remaining constants is we're going to use what's called equating coefficients. So these two sides of this equation, well, both of these are polynomials. The left-hand side is a first-degree polynomial. It's 3x minus 8. And the right-hand side also better be a first-degree polynomial, which is 3x minus 8. That's the only way these two things are actually equal to each other, is if they're the same polynomial on both sides. What that means is that we've got a lot of stuff over here that better cancel out the right way. So usually what I would say is, if you're trying to equate coefficients, you want to look at the highest power of x on either side. On the right-hand side, I'm not going to do it, but if we were to multiply at the right-hand side, what would the highest power of x be? Wait, that's x squared. So I know that on the left-hand side, I have how much x squared? Now, I don't see any x squareds over there, right? There's no x squared on the left. It's all right. So there's a 0x squared on the left. Now, here's where someone could argue you might actually want to multiply out the right-hand side. I disagree. I'm just going to say, well, if I multiplied out x minus 3 squared, I get x squared minus 6x plus 9. And then I have a times x squared. I don't care about the lesser powers at this moment. I don't get any x squared terms right there. And then if I multiply out this, I get c times x, which is c times x squared. And then another term which I don't care about. So looking at this, well, if I have 0x squared on the left and I have ax squared plus cx squared on the right, that means that a plus c had better equal 0. And since we know that a is negative 8/9, we can say that c is equal to negative a, which is positive 8/9. That seemed a lot easier to me than trying to deal with this garbage. Okay, so just to kind of make it a little bit more clear, in case what I've done was a little bit too quick there, here's what's really happening. You can multiply this out if you really want to. I don't want to, but I'm going to. So we multiply this out. We've got a times x squared minus 6x plus 9 plus b times x plus cx squared minus 3cx. And then you can distribute this out and say you've got 3x minus 8 equals, I'm going to combine the x squared terms together. I should distribute this out first. I've got ax squared minus 6ax plus 9a plus bx plus cx squared minus 3cx. And then finally, combining the like terms, I have a plus c times x squared. I have, there's an x, there's an x, there's an x. So I have bx minus 6ax minus 3cx. And then finally, my constant term, 9a. So here's what you could say if you want to do it this way. You could say, 1, a plus c better equals 0 because there's a 0x squared on the left. 2, b minus 6a minus b minus 6a minus 3c equals 3 because the coefficient of x has to match. And finally, something we actually did use, 9a has to equal negative 8. We got that by setting x equal to 0. So a equals negative 8 over 9. And then c has to equal positive 8 over 9. And then you could plug in a and c and solve for b. But again, we didn't need to do that because we already found b an easier way. So here's what I would say about finding these constants. Do the easy thing first. Use all your nice convenient values of x, in this case, x equals 3 and x equals 1, to find whatever you can. And then if you run out and still have things left to find, then start equating coefficients of, I would always start with the highest power of x you've got on either side. You might not have it on both sides, and then work your way down. And then you have to remember that you still have to finish the problem, right? We're not done yet. So then we found A, B, and C. C was positive 8 over 9. So then I guess I can use this paper over here. So then we're going to go back and rewrite the integral, which I'll remind you, it was the integral of 3x minus 8 over x times x minus 3 squared. And it was going to equal a over x plus b over x minus 3 squared plus c over x minus 3. And our a value was negative 8 over 9. Our b value was, I think, 1/3. And our c value was positive 8 over 9. And of course, if I'm writing an integral is equal to an integral, I should probably write the integral. Two of these should be, in my opinion, relatively straightforward because they're division by x to a first power, this part and this part here. This one we should rewrite. So I'm going to think of this as, I don't really want to rewrite all of it. So here, let's just do this instead. We should be thinking about this. Okay, this here, we were thinking, hey, we can rewrite that as 1/3 times x minus 3 to the negative 2 power, which we can just use the anti-power rule to anti-differentiate. Technically, you could do a u sub, but if you're letting u equal x minus 3, your du is just going to be dx, so I don't think you need to do the u sub here. So here's what we're going to get. We're going to get negative 8/9 times the antiderivative of 1 over x is the natural log of the absolute value of x. Plus, okay, here we're integrating 1/3 x to the negative 2. We're going to get 1/3 x minus 3 to the negative 2. We're going to get 1/3 times x minus 3 to the negative 1 divided by negative 1, Right, we're adding 1 to the power, dividing by the new power. And then thirdly, we're going to get 8/9 times the integral of 1 over x minus 3 is the natural log of the absolute value of x minus 3, plus c, of course. And although I hate not simplifying this here, if it was on an exam, you should just leave it like that. Even though it would be super easy to simplify, don't waste your time. Time is it? Speaking of wasting, oh my gosh, time just flies. Okay, so I should ask you all, did either of your instructors talk about what happens when you have an irreducible quadratic factor? Meaning you have something like the integral of, let me grab my example here instead of just making one up. The integral of x plus 1 over x times x squared plus 1. Cool. All right. So when you have an irreducible quadratic factor, the decomposition's a little bit different. So the number, I forget what it was, 3. So for something like this, you're still going to start off the same way. Well, it's, I mean, I should point out, it's already especially if it's already factored for you. It's already factored for you. That's probably a pretty good time that you're meant to do partial fractions. Even then, I'm still going to multiply it out real quick. Okay, x cubed plus x, the derivative is 3x squared plus 1. Definitely not a u substitution. Or u equal x squared plus 1, still not going to be good because your du would be 2x, and definitely we don't have that on top. So we're certainly thinking partial fractions. So we're going to let our fraction x plus 1 over x times x squared plus 1 equal. So for the x to the first, we just get an a over x. And for the x squared plus 1, I want to really emphasize here, x squared plus 1, it's called an irreducible quadratic factor because it cannot be factored. Another way to think about it is that quadratic never crosses the x-axis. It doesn't have any real zeros. So you can't factor x squared plus 1 without using imaginary numbers, and we're not using imaginary numbers. That's not until 17C. But you can't factor x squared plus 1, so we have to write it as just x squared plus 1 all by itself on the bottom. And when it's an irreducible quadratic, you don't just get a constant on top. You get a linear function with constants. So you get a bx plus c. And the reason why is because, I mean, this can sound kind of annoying. The reason why is because it works. And it's been proven that you need this to make it work. But I would say the reason why is because it doesn't work if you don't have it. So the problem here is if you just wrote a over x plus b over x squared plus 1 and then tried to solve for a and b, you would get either a or b having to be 2 different values, which doesn't work. You need it to be 1 value because it just wouldn't work out the right way. So we're going to deal with it the same way we dealt with the other thing. We're just going to multiply both sides by the common denominator. I should back up here just to make sure. So when you have like an x squared plus 1 or an x squared plus 4 or an x squared plus 9, usually it's an x squared plus a square number. It doesn't have to be square, but it's nicer when it is. You're always going to have a constant times x plus a constant over that thing. All right, so now usual process. We're going to multiply both sides by the common denominator. Instead of writing another line, let's just write it up here. So we're going to multiply both sides by x times x squared plus 1. On the left-hand side, we should just get x plus 1 because we know the denominators fully cancel out. On the right-hand side, when you multiply by a over x, the x's cancel, and you get a times x squared plus 1. And then when you multiply by bx plus c over x squared plus 1, the x squared plus 1's cancel, and you get bx plus c in parentheses times just x. Okay, let's use up our convenient value, singular. There is only one nice value of x here. It's 0. So if I plug in x equal to 0, I get 0 plus 1 on the left equal to a times 0 plus 1 plus b times 0 plus c times 0, right? This whole term is just 0 over there. So a equals 1. Cool. How nice. And now we're out of values. So now we're going to do the other thing where we equate coefficients. This one's probably not terrible enough that we could actually just multiply the whole thing out. So if we multiply out the whole right side, I'm going to have x plus 1 equal to ax squared plus a plus bx times x is bx squared plus cx. And then we can fill in the value, wait, we should fill in the value for A that we already know. So what we really have is x plus 1 equals A plus B times x squared, but that's really 1 plus B times x squared. And then we have C times x, and we have A. So clearly, maybe not clear, I'm going to make it clear. A has to equal 1, which we already found. Oh, I should have written 1 there. Sorry, I should have written 1 there. So 1. And then definitely 1 plus B has to equal 0 because there's 0x squared on the left. So 0 equals 1 plus B. That's going to give me B equal to -1. And then C better equal the coefficient of x, which is 1. So C equals 1. Not too terrible. Again, it's more terrible sometimes depending on the function you got. Okay. So definitely be aware, occasionally someone will ask you just to write a partial fraction decomposition and not actually do the integral. So I'll say one of the most important tips you can ever hear about taking a test is to read the instructions slowly and carefully for every problem. As someone I've known and respect well says often, go slow so you can go fast. Read the instructions slowly and carefully so that then you can work through the problem knowing all the things you're supposed to be looking for and doing. So we still have to finish this problem. We're going to rewrite this integral of x plus 1 over x times x squared plus 1 as the integral of 1 over x plus negative x plus 1 over x squared plus 1. Okay, here's the deal with this irreducible quadratic factor thing. You always, always, always have to break it up. You cannot deal with it otherwise. You have to break this up as negative x over x squared plus 1 plus 1 over x squared plus 1. It is an absolute must. There are no ifs, ands, or buts. So we're going to rewrite this as the integral of 1 over x dx plus the integral of negative x over x squared plus 1 dx plus the integral of 1 over x squared plus 1 dx. Here's what's always going to happen. The multiple of x over x squared plus 1 is always going to be a u substitution every time. The constant over x squared plus 1 or x squared plus whatever is always going to be the arctangent of something. That's how it's always going to work every time if you have this one of this thing over x squared plus 1. The only exceptions to that are if either b or c happen to be 0. Then you don't have to break it up because there's only one piece anyway. So let's see, writing this out. Let's just do the u sub over here real quick. If my u is x squared plus 1, my du is 2x dx, 1/2 du equals x dx. So I'm going to rewrite this integral as the integral of negative x dx is going to be 1/2 du. So it's negative 1/2 du over u. And that integral is going to be negative 1/2 natural log of the absolute value of u. So writing out my full answer over here, the integral of 1 over x is the natural log of the absolute value of x. We just found that the integral of negative x over x squared plus 1 is negative 1/2 natural log of the absolute value of x squared plus 1. We'll check that in a second. Plus the integral of 1 over x squared plus 1, that is exactly the derivative of the arctangent of x, so the integral is the arctangent of x plus c. Point of interest, or just to check your work, if you take the derivative of the natural log of x squared plus 1, or in general, the derivative of the natural log of some stuff, you get 1 over the stuff times the derivative of the stuff. So the derivative of the natural log of x squared plus 1 is going to be 1 over x squared plus 1 times 2x, and the negative 1/2 times 2x gives us the negative x on top. So that is the correct antiderivative. No, I shouldn't do that. Yeah. And time just flies right on by. So I think that's, oh yeah, we should do one more because you never know. Sure, let's do, yeah. I said I was going to get some U sub and or integration by parts problems. Well, that was clearly a lie because we're not going to. I wanted to, but we didn't. I should point out on Monday, I know some of you have an exam before class meets and some of you have an exam after class meets. So to that end, we're not going to be doing like exam review on Monday because like some of you are already going to take an exam, but we'll still be covering content that's probably relevant for your exam. So you should still come, obviously, whether or not you've taken your exam already or haven't. So let's look at, sure, two more problems. So let's look at this integral, the integral of x squared minus 1 divided by x squared minus 4. And what I want to point out here is we can't right off the bat use partial fractions because the degree on top is not smaller than the degree on the bottom, right? It's equal to. So here, the first step, if you can't do a U sub, which we can't, is to do polynomial division. So boy, can you spell polynomial? Polynomial division, which is not very interesting in this example, but we're still going to do it. So it's x squared minus 1 divided by x squared minus 4. And then you ask yourself, what do you multiply by x to the highest power to get x to the highest power? Well, in this case, 1. 1 times x squared minus 4 is x squared minus 4. Subtract, and then x squared minus x squared is 0. Negative 1 minus negative 4 is positive 3. And then if the remainder has a degree that's less than your divisor, you stop. So typically, whatever the difference in degrees is how many times you're going to have to do this, right? If the difference is 0, I should say, the difference in degrees plus 1 is the number of times you'll have to do this. So if the difference is 0, you'll have to do it once. If the difference is 1, you'll have to do it twice, and so on and so on. So here, we're going to rewrite our integral as the integral of 1, the quotient, plus the remainder 3 divided by the divisor. The way you should think about this, which I think is kind of clever if I do say so myself, is 3 still has to get divided by x squared minus 4. So we should be writing 3 divided by x squared minus 4. But the 1 is what you got by dividing them. So it's the thing you got plus the thing that still has to be divided by the thing you're dividing by. And now we can say this is the integral. Well, sorry. I'm going to say the integral of 1 is just x. And then to integrate 3 over x squared minus 4, now we are going to have to use partial fractions because that definitely factors and there isn't a u sub there. So for 3 over x minus 2 times x plus 2, we're going to set that equal to a over x minus 2 plus b over x plus 2. Any order you want to write them in, it doesn't matter. I just pick what I see first typically, but it doesn't matter what order you write them in. Not showing my work, multiplying both sides by the common denominator. The left side I'm going to get 3. The right side I'm going to get a times x plus 2 because the x minus 2's would cancel. I'm going to get b times x minus 2 because the x plus 2's would cancel. And then we start plugging in our nice values of x. We're going to plug in x equal to negative 2. We're going to get, there's nowhere to plug it in on the left. That's okay. We still have a 3 there. So we're going to get 3 equal to a times 0 plus b times negative 2 minus 2. So 3 equals b times negative 4. So 3 divided by negative 4, or negative 3 over 4, is equal to b. Similarly, if we plug in x equal to positive 2, we have 3 on the left. We have a times 4 plus b times 0. So 3 over 4 is going to equal a. So then we can say their integral is going to end up equaling, don't forget about this x out in front, x plus, instead of the integral of 3 over x minus 2 times x plus 2, it's going to be the integral of 3/4 over x minus 2. And instead of writing plus, let's just say it's minus 3/4 over x plus 2. And we're going to integrate, and the x still is just hanging out because we already integrated 1 to get x, plus 3/4 times the natural log of the opposite value of x minus 2, minus 3/4 times the natural log of the opposite value of x plus 2, plus c. All right, let's do one more. I feel like the polynomial division ones are never that easy, personally. So let's look at something a little bit more complicated, like, sure. Let's look at the integral of x cubed over x squared minus 2x plus 1. That's moderately annoying. So clearly we have to do the division, right? Because the degree on top is bigger. So we're going to have x squared, sorry, we're going to have x cubed divided by x squared minus 2x plus 1. And normally when we're doing polynomial division, if you find it helpful, it's certainly not necessary, but I find it very helpful to write in the missing powers of x. So I'm going to write plus 0x squared plus 0x plus 0. To me, that just helps me make sure I keep things lined up. So then what am I going to multiply by x squared to get x cubed? X, of course. X times x squared is x cubed. X times negative 2x is minus 2x squared. X times 1 is plus x. Look how nicely things are lined up. You're welcome to do the thing where you change the signs of everything. I hate doing that. I think, to me, it just feels wrong. I know I'm subtracting. X cubed minus x cubed is 0. 0 minus negative 2 is positive 2x squared. And 0 minus x is negative x. Bring down the 0. Degrees match, so we got to do it again. So now you multiply x squared by 2 to get 2x squared. So 2 times x squared is 2x squared. 2 times negative 2x is negative 4x. 2 times 1 is 2. Subtract. That minus that should always be 0. Negative x minus negative 4x is negative x plus 4x, which is 3x. And 0 minus 2 is negative 2. Okay, so we're going to rewrite this integral as the integral of x plus 2 plus something divided by something. What goes on top? What does go on top? What still is getting divided? The 3x minus 2, right? You still have to divide 3x minus 2 by that. So we have 3x minus 2 divided by, I'm going to factor this. X squared minus 2x plus 1. I'm not going to factor it yet because I want to point something out. So at this stage, be extra careful. Sometimes people do something tricky and they make it so this is just a nice U sub. So when you get to this place here, like if this was like a 2x minus 2 on top instead of a 3x minus 2, that would exactly be the derivative of the bottom. So keep your eye out for a U substitution here. It could happen. It's not going to happen here. So we're going to do this part, the partial fraction decomposition of 3x minus 2 over x minus 1 times x minus 1. Oh, that's interesting. X minus 1 squared. So we're going to have an a over x minus 1 squared plus a b over x minus 1. Kind of funky. Yeah, I hesitate. Technically, you could also do you could do this integral differently, actually. I will say the integral of 3x minus 2 over x minus 1 squared, you could do it as a u sub with a back sub. That's probably not my preference, though. But either one's kind of terrible. So, but you let u equal x minus 1, and then du would be just dx, and then your numerator would be like 3 times u plus 1. Yeah, it's well, maybe I'll show you both ways. Probably not, though. So anyway, we're going to do this. We've got 3x minus 2. We're multiplying both sides by x minus 1 squared. We're going to get a plus b times x minus 1. And I would actually point out here, I think it's really easy to see what everything is without doing anything else. Show me on your fingers. What does b have to be? On your fingers. Let's see. So b times x on the right. And how much x do I have on the left? B's got to be 3. There's no other choice. That's the only place you're getting your x's on the right-hand side. So b better be 3. And, well, then a I have to work for, I guess. So I guess I could have plugged in 1, right? If I plug in 1, I get 3 minus 2, which is 1, and I get b times 0, so a has got to be 1. But it was easy to see b. All right, so then we're going to rewrite this as the integral of x plus 2 plus, all right, I'm going to make a change here. Instead of writing 1 over x minus 1 squared, since I know I'm going to have to bring that up to the numerator, I'm going to write 1 times x minus 1 to the negative 2. And then plus 3 over x minus 1. Integrating that, we get x squared over 2 plus 2x plus x minus 1 to the negative 2 plus 1 over negative 2 plus 1 plus 3 times the natural log of the absolute value of x minus 1 plus c. That's it. If you care to know how you can, so just so everybody knows, I will point out you could have done, I'm not going to do it because we are literally out of time, but if you wanted to, you could have done 3x minus 2 over x minus 1 squared. You could have done u equal to x minus 1, du equal to dx, and then rewritten it as the integral of du over u squared, and then the numerator you have to replace the x with, you have to do a back substitution and say that u plus 1 is equal to x. So the numerator is 3 times u plus 1 minus 2. And then you simplify the top and divide each thing by u squared, and then you integrate each thing. And your answer should look mostly the same. Good luck on your test for those of you I won't see before then. Good luck for those of you that I will as well.